Yes.
So,
Yep.
welcome to the story of the I-35 bridge collapse, and it's basically the project involves BIM conversion to City GML, and then talking about adding value to that with adding in linked data and doing some analysis there. So, we've got a lot of ground to cover today, so I'll just jump right into it. Here's our agenda, sort of a bottom-up view here. So we'll do some brief introduction, introduce everybody that's on the call, and then I'll talk a little bit about FME and 3D, introducing some City GML concepts. And then Alex is going to give us a bit of an overview of the project. Raj will talk about the modeling in Revit, and then Lutz or I'll cover the FME conversion from BIM to City GML, and then we'll do some exploration of the model with Lutz before we hand it over to Alex, who's going to look at some of this semantic web linked data analysis. So that's, yeah, so we've got a pretty ambitious agenda. We'll go through and cover as much as we can. And anything that we don't have time to cover, we will have the presentation and examples available for download as well. So let me introduce everybody here, just starting at the top. So Raj Banga from DBI Architects, if you can just say hello.
Hello, everybody. Good morning.
So as you heard, he's dialing in from DC. And then we have Alex Carmen. He's also from that area. I guess you're in Virginia right now, Alex?
That's right, from Reston. Hello, everybody.
Revolutionary Machines. And then Lutz from Virtual City Systems from Berlin, if you want to say hello.
Hello, everybody.
And then, of course, I'm from Safe Software. So yeah, a bit of a collaboration going on here.
Covering a good part of the globe.
Yeah. We should have had Ken supporting us from Europe on the QA, but just to round it out. So we also have Dave and Mark helping us out. Dave's one of our resident BIM experts, so if you do have any questions, feel free to ask. Mark's just sort of an overall all-around expert, so they'll be around in the background to answer any questions you have. So there is a question tool. Feel free to make use of that. And so why don't we go ahead and launch the first poll question. We're just kind of curious as to how much experience you have with both FME and BIM, just to get a feel for the audience. Yeah, so it looks like it's a fairly even spread between people who are using FME and BIM, or just BIM and not FME, and those of you who are new to FME. So. Okay, so if you are new to FME, there's a lot of great resources online. You can just go to safe.com and click on the support learning resources there, and here's a link for the getting started resources. So feel free to make use of that. And I don't have time to get a lot into background on FME given our dense program, but just in a nutshell, we really, our main focus is on, I guess a lot of people know about us from our data conversion, so we can move data between almost any format you can imagine related to spatial data, as you can see from that range there, as well as supporting a lot of different non-spatial formats, things that you wouldn't normally think of when you think of things like CAD and GIS, so Excel spreadsheets and data. Started off with CAD to GIS, and then we added support for things like raster databases, point cloud. So really covering the whole gamut of what's possible with spatial data. And then very quickly we realized that the conversion is just the start of the problem. The real tough problem is usually the data transformation piece, so transforming your geometry and your attributes. So we have a lot of tools that support that. And then overall, we have tools that allow you to integrate between different vendor applications and ultimately do have things like FME Server to support your enterprise level workflow integrations. So 400 plus formats. Wow, I didn't realize the number was that high. I haven't been tracking that lately. So that's quite a few. And certainly when you start talking about 3D models, you do need a lot of those formats, and then data transformation. So here's a few, as just a quick snapshot of some of the 3D formats that we support. And we recently added Revit Reading, which we'll see today. And we're working on, for example, IFC writing for 2015. So hopefully that's coming along. So those of you who are interested in that, stay tuned with 2015. And there's a lot of other formats, as I mentioned, that come into play when you're dealing with 3D or BIM data. So that, obviously you have to bring in point clouds, and there may be raster data required for draping and what have you. So yeah, a lot of growth there in recent years. And just a few of the FME tools for tackling 3D. Obviously, there's the translation, but there's also schema mapping, geometry conversion, and things like reprojection and vertical datum support that you require. And ultimately, we have to have a complex geometry model that allows us to model whatever complex solids, multi-surfaces, and aggregates, being able to support all of that. So one of the main workflows is going from 2D to 3D. And as I mentioned, some of the formats we support: SketchUp, IFC, and point clouds. And we don't have time to get into point clouds, but there's some great resources and webinars specifically just on that. And yeah, other workflows related to BIM, we'll see some visualization today. So simply being able to bring up that data in 3D and inspect it and turn things on and off, that's pretty important. Sometimes you want to go the other way, so you may have a 3D model and you want to have different views of it, maybe a profile view or a plan view for a floor plan, and then using that for route planning. There's a lot of other analysis you can get into with BIM. So you may have a very complex model, and all you care about are the building spaces for doing things like energy efficiency management and optimization. And if you have all this great 3D data, you might want to share it as well. And so we can allow conversion into a lot of more consumer-friendly formats, things like KML and PDF. So what's your interest in BIM? If you can run the next poll question. So just let us know what best fits. And if for some reason your category is not on there at all, feel free to just make a comment in the Q&A box, in the question box, and say, I'm working in this area. Okay, so we've got quite a few people from engineering and architecture and facilities management, and then a few from the other categories as well. Thanks for your feedback. Okay, so just a couple of words about CityGML, and then we'll get into. Then I'll hand it over to Alex. He'll talk about this particular project. CityGML, one of the main motivations there is that more and more organizations are wanting models in order to model things in 3D, and CityGML there was really a need to have an exchange format that allows for integration that was basically vendor independent. So there's lots of possible applications areas similar to the categories in the poll questions, so things like urban planning, disaster management, environmental simulations, energy, and ultimately it's about, and Alex will get into this a lot more later, but the whole idea that we need to model things semantically. So it's not just about having a complex 3D model that you see at a trade show, where you've got this essentially some kind of video game or simulation you can fly through, but you have no idea what's behind that wall or what the purpose of that building is. So capturing the semantic information or the meaning of what the different objects in the 3D model correspond to, that's really key to make this usable for different exchange of data, so it's not really optimized for visualization, and so that's why, for example, the tools that Lutz will demonstrate make it a lot better for visualization. So it's mostly focused on exchange, and it's really all about modeling all the relevant parts at the city scale. So clearly the city scale is different than the BIM being building focused. So there's some simplification and transformation that has to happen. But yeah, all the different layers, as you'll see, are focused at the city scale. And it's all built on GML3. So the basic idea is there that it's modular. There's a coherence between the semantics and the geometry. So buildings are solids, building parts are solids, wall surfaces might be composite surfaces, etc. So there's that correspondence. And the other key concept is level of detail. So you can have just a 2D view, LOD0, simple block model, LOD1, all the way up to a complex model with the detailed interiors. So that really can help different use cases where you maybe want a view from a mobile device or from a workstation. And as we'll see today, there's support for things like external references because you can't fit everything. No model is complete. It can encompass all the details you might want, so having support for external references is important. You can texture things with raster or different types of textures, and ADE, that allows you to extend the schema for particular applications such as energy or noise. So here's just some examples of the different themes, and whether it's water or bridge, railway, different transportation, things like that. And in terms of our support, I think we've got pretty comprehensive support. We've particularly our user community out in Europe, they've kept us busy with, for example, these ADEs. So I've worked with the Dutch IMGO 3D NL project and Inspire, and so we do support those ADEs. We support CityGML version 2.0, and then of course everything before it, and all the different level of detail. So this is just a view of what it might be like to read a CityGML data set. You can see the city model building and then the more detailed components like wall surfaces. And here's some typical workflows, just everything from simple data inspection to generating or writing out 3D CityGML models, creating different levels of detail. Often, let's say in the 2D to 3D conversion process, you may need to drape for 2.5D or for surfaces, or do extrusion to support 3D. And then today, of course, we were going to see examples of BIM to GIS. And I won't go. We don't have time to go into a lot of detail on how to write CityGML. So there's quite a few resources online for that. But the basic idea is that you do need to set for each object, you need to set what the LOD name is, and you need to set the feature role, as well as do the map to the appropriate feature type. So this is just what a snippet of CityGML might look like. And here's an example of IFC to CityGML conversion. So often there's a geometry transformation involved to fit what CityGML requires, and some schema mapping to populate things like IDs and also georeferencing. We've got quite a few transformers to support building up or doing that transformation. And for the key thing here is you can see that we have to set the LOD name. So in this case, it's LOD4 multi-surface, and the role of the feature. So in this case, it's a bounded surface. And then things like setting IDs. So just typical FME stuff there. And this is a demo that this group we collectively worked on a year ago on Leesburg Courthouse. So Maybe, Lutz, if you can speak to this, here's just some examples of where CityGML is being used. I don't know if you can quickly summarize this, Lutz.
Maybe short summary would be that we have a very fast-growing adoption in Europe, in Germany, in the Netherlands. This is driven by EU directives, and then we see further examples in the Near East and also in Far East. So Sultanate of Bahrain and Singapore lately started to work with CityGML, and we find this a very fascinating future for CityGML.
Okay, yeah, thanks, Lutz. Yeah, we're seeing adoption around the world, and interestingly, CityGML is relatively new in North America, but internationally it's been used quite extensively already. And as you mentioned, yeah, the push at the governmental level to do mapping in 3D by the various mapping agencies, particularly in Germany and in Holland, has certainly pushed the evolution of CityGML.
Yeah.
So just one or two quick words. We also have tools for 3D validation, geometry validation, and that even support repair. And so there's a lot of different geometry tests you can do. Unfortunately, not all our source data is perfect, so sometimes we do have to clean it up. And as I mentioned earlier, 3D data distribution. So if you've got these great models, you want to share them, don't hide them. So just to summarize quickly, and then I'll hand it over to Alex. FME does provide a wide range of tools to support 3D and CityGML. Everything from reading and writing CityGML, translating to and from the wide array of 2D and 3D formats that we support. And then letting you get at the nuts and bolts of the schema and geometry, because often there are changes required there. Validation of the schema, geometry, and semantics. So you can start out as simple and get as complex as you want with that. And ultimately, we don't have time today, but there's lots of tools that FME has through FME Server to support automation and enterprise services, and ultimately publishing out that 3D data to support whatever services you might want. So we'll hand it over to Alex, and Alex is just going to describe the project that we've been working on.
All right. Can you see my screen, Dean?
Yeah, looks clear.
All right, good. I apologize, guys. I use the designer mode so I know where I'm going. If I maximize it, I'll get lost. So my name's Alex Carman. I'm co-founder and CTO of Revolutionary Machines here in Reston, Virginia. And our company develops solutions for the semantic web and data science and the Internet of Things. We're excited to be here today with our partners Safe Software, DBI Architects, and Virtual City Systems to demonstrate the proof of concept today with you. And it's a pretty exciting concept. We call it the universal index of the physical world. What we want to do is we want to use CityGML, which Dean has described to you as it's a semantic XML format. We want to use CityGML not as data, but as a special, visible, browsable 3D index to even more data. So we do this by embedding semantic links called URIs. That stands for Uniform Resource Identifier. We embed semantic links in the CityGML. So rather than try to put data in the CityGML, we just put links to the data in the CityGML. And those links point over the internet using the free HTTP backbone of the internet to external semantic RDF databases, and they point in various ways to each other. So you wind up with you wind up able to link far more data and provide a far richer context, a business context, around the engineered structure than if we try to put the data directly into the CityGML file. It's also far more agile because subject matter experts can just concentrate on managing the data that they know about. But nevertheless, as soon as they post new data, everyone else can find it and mix it and match it and merge it without having to share schemas and software releases and stuff like that. And we call that, in the semantic web world, that's called cooperation without coordination. Everyone can participate together without having to decide on table definitions and column definitions and primary key, foreign key relationships and stuff like that. And we believe that the universal index of the physical world, as we call it, is the big data solution for 3D urban environment because the solution scales and because it's very, very agile. So let's dive into what we're talking about here. I think that we all know that we live in a physical world. Probably almost every one of us, whatever our profession is, we perform it in some sort of a building. And our lives intersect in that building. So whether you're a doctor or a lawyer or an accountant, you may work in the same building. You have different jobs and you use different databases and different software, but you're all located in the same building. It would be nice if you're using an engineering tool to be able to know at least something about all of the tenants in the building, but you wouldn't want to have all the data that they use in the building model. You wouldn't want to know everything about every client that the lawyer has or every patient that the doctor has, but you would want to at least know some information. And so, the ability, this new paradigm where we just put pointers to the data into the building model is really frees us up to be able to share the things that we want to share and to be able to interact just like we do in our real life. We should be able to do that with the software. So what that does for us, by embedding semantic links in the data, we reduce a lot of the costs involved because we can get software to talk to each other over the free internet HTTP backbone of the internet. So there's a lot of software savings there, but there's also a lot of time and labor savings because you don't have to coordinate, massive Uber schemas of 400 different database tables and that sort of thing in a relational model before people can even share the information. And the information becomes a lot more accessible to a lot more people, and the business owners themselves get to be the subject matter experts, and they get to manage their own data without having to go through an intermediary gatekeeper like a database administrator or somebody like that. Because the semantic links are meant to find out, to discover the existence of relevant information and access it over the internet without a lot of intervention or mediation. That's a lot of words on that slide, so I'll skip it. So, for instance, you'll see later Raj will have a couple screenshots where he's looking at this bridge model inside of Revit. And by embedding semantic links, Revit wouldn't have to have feature creep and bloat and have more and more menu options and context options and drop-down list boxes and things like that in order to be able to handle what I call ancillary data. The data is not about the building itself and what keeps it up, or the bridge itself and what keeps it up, but the ancillary data is about the uses and the relevance of the structure. Your engineering design tools won't have to have this arms race in order to keep up with being able to handle ancillary data, and you won't have to be trained in how to use more and more features that you see once in a class and you'll never find again. And also, we want it to be an automated system where you have machine-to-machine spiders and crawlers that can find out relationships and deliver them to you in an asynchronous sort of delivery paradigm. So what we wanted to do is we wanted to come up with an example where you can see the scalability and agility of the system in use. So we concentrated on the 2007 August 1st collapse of the I-35 West bridge in Minneapolis that spans the Mississippi River. If you remember, one morning, it just collapsed. So the National Transportation Safety Board collected a lot of information about that. They created what they call an accident investigation, And in the course of their work, they collected over 5,000 documents and over, I think it was 34 DVDs of digital information about the bridge. So obviously that's a good example of one structure, one engineered structure, a bridge, where you wouldn't possibly want to embed hyperlinks in the CityGML for absolutely all of those documents. Instead, you want to do the reverse. You want to link the bridge to the documents, not the documents to the bridge. And that establishes a business context, and that can scale exponentially. And that's what we hope to be able to show to you today. In an hour format, the exercises are all available online. We're not going to be able to get to the exercises, but I assure you there's just 2 zip files you need to unzip and you're good to go. There's 15 spoon-fed exercises there, and you'll see immediately the amazing network effect of embedding semantic links inside the CityGML. So we talked about that. So what we're going to do today, what we'll show you through several presenters, is we took the 1965 original blueprints, and DBI architects very patiently and diligently digitized that and turned that into a Revit model. And then Dean's going to transform that Revit model into CityGML in FME Desktop. At Revolutionary Machines, we ontologized not all of the information, but we ontologized a substantial portion of the documentary evidence of the bridge collapse, and we make all those materials, the ontology and all the documentation is available online for you to experiment with. And we embedded URIs linking our ontology to the bridge. We embedded those inside the CityGML model, and you'll get a chance to take a look at what those look like. And then the exercises that you can do after the workshop is you'll run Sparkle queries, and Sparkle is the query language for semantic data. It looks a lot like SQL. If you've ever seen SQL, there's times when you can't tell the difference between Sparkle and SQL. They use the same vocabulary. And you'll be able to see for yourself that using CityGML as an index, sort of like using the bridge model as sort of like a card catalog rather than a document, becomes far, far more capable of reaching out to all kinds of different data that has to do with a lot of different disciplines and roles in society. We also, this is really the tale of 2 bridges. There's the old bridge that fell down, and we ontologized that. And there's also the new bridge that replaced it. They built it a year later in 2008. And as an exercise to show you that you can go between tabular data to RDF, to semantic data, and then back to tabular data again, we ontologized the Federal Highway Association's inspection record for the new bridge. The National Bridge Inventory has basically ASCII files, comma delimited files for yearly inspections of every bridge and overpass in the United States. There's over 300,000 of them. Each record has 116 fields of data, and in the exercises, you'll be able to go back and forth between the tabular representation of the data and semantic data. But it's while it's in the format of semantic data that it has a larger business context, and you can also reach out to other data sources about the bridge. For instance, DBpedia or Wikipedia or something like that. The tools that are used in this workshop, you'll see Virtual City Systems, their Virtual City Map, browser-based 3D view of the bridge. You'll see FME Desktop presented by Dean. You'll see Revit presented by Raj. The 2 things that you would download in order to visualize and inspect and play with the ontology of the bridge is Protege. You just go to stanford.edu and download it and unzip it, and you're good to go. And Jenna, which is an Apache project, go to Apache Foundation and download Jenna. Just unzip it, and you're good to go. And that allows you to perform Sparkle queries, including federated queries across the internet to other websites. So the materials will be on our website. They'll be on DBpedia. If you don't know this, everyone's familiar with Wikipedia. There's a similar site meant for machines, not humans, called DBpedia. So for every article on Wikipedia that a human reads in HTML, there is an equivalent parallel version of it in RDF triples for machines to read called DBpedia. So you'll be experimenting with querying that information. So I guess that's it. I can hand it back to, it'll be, I can hand presenter mode to Raj. And Raj
No, that's okay. I'll take care of the presenter mode.
Okay.
So I'll take over the presentation, and then Raj can just speak to his slides. So let me just maximize this. So I'll just hand it over to you, Raj. Take it away.
Dean and Alex, thank you very much. This is Raj Banga here with DBI Architects. Just a little quick introduction about myself and the firm. I'm a director here at in our Virginia Reston office. My career has taken me sort of in and out of the profession, specifically devoted to architecture, and then I've spent maybe a decade or so outside of the direct work of architecture and in the technology aspect of it. I've been a part of 2 different startup companies dealing with mobile technology, and you know, this world of BIM that we're embarking on right now really has some incredibly interesting opportunities, and so we're very, very proud to be working with Dean and Lutz and Alex on what the future holds for City GML, especially as Dean pointed out, you know, as it starts to make its way over here into North America. Dean, if you could just go to the next slide there, I'll talk a little bit about the firm. We are a firm based here in the Washington, D.C. metro area. We're about 60, between 60 and 70 people. There's an office in downtown D.C. and one out here in Reston, Virginia, which is about half an hour outside of the city. We're predominantly a commercial interiors group. I'd say about 70% of our work is interiors focused, both in the private sector for developers, building owners, end users, and in the public sector. A lot of work we do for the government, and most of that work ends up, I'd say in the past, you know, 8 to 10 years has been really focused towards the security and intelligence-based agencies. However, you know, other agencies like the National Endowment for the Arts and Humanities, we've just done work for them too, and so it goes across all agencies in the public sector. Some of the institutional sector work that we're focused with is World Bank, IMF. We've done work for those agencies as well as some other institutional groups. We do have an architecture group here. That's about 30% of our work, but it appears to be growing every year, and we're very excited about that. And we do a lot of master and urban planning work as well. One of the things that Dean showed you earlier on in this presentation was a quick shot of this project we're currently getting underway here in downtown Leesburg, which is in Loudoun County. That is hopefully going to be one of the upcoming seminars where we're going to take this technology and show you how we transform its use into a different kind of structure other than the bridge. Just a quick bit about the design technology here at DBI. You know, we feel that we are not just early adopters, but some leaders in how our industry utilizes CAD and BIM technology. You know, I think we had one of the first CAD digitizer stations back in the late 70s and 80s. I think the thing must have cost $20,000. And obviously that technology has just become so ubiquitous in our industry that we're now doing some fantastic things and working with renderers and other ends of the country where we can just do great stuff within a matter of 24 hours. Right now, about 90% of our work is in Autodesk Revit architecture. For those of you that are listening in on and don't exactly know what Revit is, it is an Autodesk product. Revit has a number of different verticals, if you will. There's architecture, there's mechanical, electrical, plumbing, structural. Although we're looking at a bridge, we did not use the Revit structural program. We used Revit architecture. And I'll sort of explain quickly how that even helped to benefit this study. So we're focused on really looking towards the future with how to integrate BIM with our clients, our partners, vendors, and the promise that it holds for just deeper, more robust collaboration. And so we're really focused right now on how to use this technology. Just to be sure that everyone understands, BIM is building information modeling. It is not, you know, a specific product, but it is really more the process of creating a digital representation of, the physical and functional characteristics of some sort of built structure, whether it be a bridge, tunnel, building, whatever you may have. That's really what BIM is about. So, Dean, if you could just toggle into the next slide there for me. So, with regards to this bridge, what we did, as Alex mentioned earlier, is he was able to get his hands on the original blueprint. There were about 95 drawings in that set. We reconstructed, we basically built a geometric representation of this bridge. All the components of the bridge, the concrete pilings, the trusses, gusset plates, road surfaces, all of these components were modeled using Revit architecture. Specifically, we're using the 2013 version. Incidentally, we're upgrading to the 2015 in about 2 weeks here, so staff's all excited about that. By using Revit architecture and for the purposes of getting this bridge built with the tools that we had available, as well as maybe the simplicity of getting this transferred over to Dean and his team with FME, there were no specific structural calculations that we used. This was a bridge that was designed and built way back in the 60s, so there was really no need for that, but it's good to know that there are no hidden calculations or algorithms within this digital model. The intent here was really to just reconstruct the geometry of it, and then we would explore how FME and CityGML we could attach data to some of the components of this bridge. Again, specifically, we were focused on the individual component that was the source of the failure of the bridge. So to that point, I'd like to go to that next slide and just talk about some quick facts about this bridge. The bridge was, actually, I'm sorry, thanks, Dean. This is a screenshot of the Revit interface. Just some things to kind of anecdotally note here. Revit utilizes, for the purposes of this conversation, there are things known as families inside of Revit. For furniture, for architecture, for building, even if you're in a different module, you use a family, which is like what AutoCAD used to call a block. We could have used a whole number of families throughout the construction, the digital construction of this bridge. However, we only focused on some specific points of the bridge, some of the trusses and the gusset plates that were uniquely tagged and ID'd so that the transfer and link to FME and subsequently CityGML would work. So there were a number of different ways to sort of skin this cat and how to build this bridge, but this is just a quick shot of how Revit works and its pull-down menus. There's a lot of great stuff here to do what we do on a day-to-day basis here. Again, just for those that may not be familiar with Revit. So, yeah, Dean, if you could just go to that last slide here. Just some of the facts about the bridge. The construction began in 1965. It took about 2 years to complete. The bridge collapsed in 2007 at a very unfortunate time. Happened to be during rush hour. But there was the bridge is over 1,900 feet long. There's 14 spans that make up this bridge, and we did model those as individual spans. 11 that make up the approach spans from the north and the south. And there are 3 different kinds of construction, too, through those spans. Some of them are deck truss construction. Some of those are known as the multi-girder construction. I think there's 9 of the north and south spans are multi-girder. And then 2 of the north-south spans were just simple concrete slab. Now, obviously, this is back in the 60s. The design and engineering of bridges has evolved and changed, and so some of this construction was very prevalent at the time. It's interesting to note that this bridge was designed with only one system. There was no redundant system as we do today. And so therefore, unfortunately, when there was a failure of real significance, the bridge collapsed. And that's effectively what happened. There's some other information here about the length of the spans and the support piers. The support piers had some actual roller, created a higher level of rigidity to the bridge. and I think that added to the failure, but ultimately the failure point was the specific U10 gusset plate. And as we proceed in the presentation, you'll see Alex and Lutz referring to how we're semantically linking data from the web. An endless array of data can be linked to the bridge, the model itself as an entirety, or to a specific component of the bridge, which would be this gusset plate. And as I said, we ID'd maybe a dozen members of the bridge here that would help facilitate the continued work that we were pursuing here with this exploration through CityGML. So that was the role that we played. I think our role here was basically to get this built so we could really start the investigation. And at this point, we air mailed it over to Dean in Vancouver, and he took it from there.
Okay, thanks a lot, Raj, and also Alex for kind of setting the stage about the project. And yeah, just thanks to DBIA for all the great work they did in building this model. So this is me, and I'll try to, the time is clicking on, so I'll try to be quick here. So basically, the workflow involved, once we have the Revit model, there's two basic steps that have to happen. First of all, within Revit, you need to use the Revit extension with the FME exporter, which if you extend Revit with FME or you install the FME plugin to Revit, it gives you this add-ins exporter option, which creates an RVZ file. That is essentially a combination of an IFC export and a bunch of supporting CSV files. And then we have a workspace that converts the RVZ to CityGML, and I'll show you that in a minute. And then finally, Virtual City Systems imports that into their system for visualization, and Revolutionary Machines does some analysis on the actual data links. So this is the basic workflow of the workspace. We're reading the RVZ file, selecting the themes of interest, because clearly it's not all themes that we want, and then georeferencing that, doing schema mapping, so mapping the feature types and attributes that are desired, setting the appropriate IDs, and then the CityGML attributes, and then embedding the URIs. So that's key to all the downstream analysis that Alex does, being able to embed those URIs. And I'll show you in a second, removing the rivets was a key process because that reduced the file size by about 85%. So this is what the workspace looks like, and you can see the input feature types there. I'll just pop out quick to the actual workspace here, and let me just have a quick look at. This is the actual bridge. So, don't have time to go through the whole workspace, of course, but one thing I wanted to point out that's really key with reading Revit is that you have this building or this data view. So this is data elements with hierarchy, and if you were to add another Revit connection, another Revit reader, there's a whole list of options here in terms of what data view you have. So this is really key when you're going from a very detailed building-oriented model to something, let's say, at the city scale or a typical GIS scale that you might use in urban planning or disaster management. You need to be able to aggregate a lot of that detail to more of a higher level data model. So there's a floor plan view, there's elements with hierarchies, which what we used here, but you can also just extract the building spaces if you were going to just, let's say, use that for energy type analysis. So you'll be able to download this workspace and run it. We'll give you the source data and everything. So I won't go through in a lot of detail. Suffice to say, kind of at the bookmark level here, there's the georeferencing. Here's some of the external references that we have. And you can see this allows us to pull in external references from a CSV file. So those get embedded in the model. And then the schema mapping. So basically we have a fairly simple CityGML version 1 type view of the data, so we don't use that many different themes. And here's an example of setting the LOD name and the feature role. And last but not least, what I'll point out here is that I'll give credit to Lutz because I did an early prototype of this, and then Lutz and his group refined it a lot. So this workspace is largely built by him. And but what problem we had was we had 15,000 or so rivets that were really slowing down the visualization. So we were able to get rid of that by using a volume calculator, and then I essentially get rid of everything that's smaller than a liter, and that made for much smaller output. So let me just zoom in here really quick. So I can spin this around, and I'll let Lutz look in his tool because it's a bit faster. But you can see the main thing I wanted to point out here isn't so much our nifty visualization. It's more just the fact that we do have this detailed data model. So in terms of how we represent the data, so you can look at the individual trusses and drill into the actual object structure of this is the solid, here's the level of detail for geometry, and the various faces and polygons that compose that solid. So yeah, this is definitely, this size model kind of dims the lights a little bit with our visualization, but you can always filter out and just visualize components of it for these very large models. Okay, so let me just get back to the PowerPoint here. So there's just a few screenshots of some of the trusses, and there's the gusset plate that failed. So just isolating that component. And I'll let Lutz take it over to look at the Virtual City Systems visualization, and just one or two other comments. We do have a new technology called jQuery, which we don't have a lot of documentation on, but it's extremely powerful, and I'm not going to teach you that today, but it basically just allows you to drill into these complex models and query or select certain things. So you could just turn on, for example, all the features on floor 3, and so that's a pretty powerful extraction tool. And yeah, I've already gone through the CityGML writing transformers and validation. So just to wrap up my bit here, and then we'll hand it over to Lutz. Some of the challenges we ran into with this project. Clearly, BIM is too complex for most applications, and so we have to isolate and aggregate. Georeferencing was a bit of a challenge because most BIM models are not georeferenced to the Earth's surface, and so we have to add that referencing in. File size was a pretty big challenge. 1.2 or 3 gigs, CityGML is not that easy to work with. So working with instance geometries is important, and in this case, removing the rivets. I've already talked about schema mapping, but yeah, in this case, we had to figure out which themes were compatible with Virtual City Systems tools, which is based on CityGML 1. And then the key thing here is also how to insert the URI references. So, which was done with those attribute creators. Okay, so let's see here. So I'll hand it over to you, Lutz.
Okay, thanks, Dean. Okay. Well, I want to make it rather short because we are a little bit running out of time. Just a few words about virtual city systems. We are a company which is focused on solutions based on CityGML. We offer consultation services, training on CityGML. We also have our own software solutions for managing CityGML data and visualizing it. And we are actively involved in the future development of CityGML. So we are chairing the OGC CityGML standards working group. And since there are not so many tools that support CityGML, we use FME a lot to transform to CityGML and from CityGML to other formats. And we have FME experts in-house and do a lot of data transformations. Maybe why CityGML? We think that as our urban environment gets more and more complex, we need semantic urban models, or we call it urban information modeling. And we think that urban information modeling is far more than 3D visualization of all the entities in the city. So the usual 3D models that you see, they are still graphical models and they don't contain any semantics. But if you want to reuse your models in different application areas, you will need or require semantic information. And so we are very excited of the potentials of CityGML because we have the possibility to store all the semantic information about the entities in an urban environment, and that will allow us to develop very smart applications in the future. Well, for the example of this I-35 West Bridge, our key ideas that we developed together with Dean and Revolutionary Machines and DBI Architect was that we want to store the model of a bridge, a database backend, and then provide a web-based interface to visually explore the bridge model. And then link the bridge to resources from World Wide Web, or maybe Alex will go more into detail about this later. And then we also have the idea of distributing, sharing the data over our web interface. So we used our existing 3D spatial data infrastructure solution. Just a very quick overview. We have a database solution that's here in the center. It's based on an open source project which is called 3D City Database, and we can import CityGML to that. And from there, we have the ability to publish CityGML or the data content of its database through a web-based authoring system to 3D web maps. We can then, from the 3D visualization on the web, query the features in the database. We are using OGC standards here. We can also integrate other data resources using WFS and WMS services. So we heavily put focus on OGC standards. And then on the other hand, for distributing data to different stakeholders, we have developed a component which allows us to automate the export of data from the database to different target formats. So this is an image of the system, and now we want to try to run it live. So what we did is we grabbed some data from USGS service to get a terrain model and some ortho imagery. Well, ortho imagery is from 2006, so it shows the bridge in the ortho imagery as well. And then we inserted the bridge model into this interface, and what we can do is that we can query these elements. If I click here on this, we serve a WS request to our database, and we will get all the external references back which are stored for this element. And this can be anything from any web page or documents, a video, and so this way we can link whatever media or resources to the bridge. Well, since the time is closing a little bit, I won't click on any more examples. We will provide the URL of this application so that everybody can try it out on its own. And I think actually that was it from my side, and I would hand it over to.
So just to clarify, Lutz, you took the CityGML that we created, it loaded into your database, and then this is basically your web service or your web server that serves up the 3D data?
Right. So
excellent.
Yeah, you can also select all the different components here. Yeah.
Very good. And then you also have the ability to generate PDFs of that, I can see. Yeah.
Yeah, well, PDF is just a screenshot, but well, what we can offer is an export functionality. I did not integrate it into this example here. Maybe Dean and Raj, if you're fine with that, we could add that to this application later.
Okay, I'm going to take the presenter back here.
Yeah.
Okay. So we're running low on time. I'm just going to go to the summary slide. I'll let Alex speak to his, and apologies to Alex for us going a bit over. So our plan is basically we're going to summarize things now, and then for those of you who do have an extra 10 to 15 minutes, we'll just keep on going after we've summarized. We'll take a minute for Q&A, and then we'll go ahead and keep going through this presentation. There was a lot in here, so you know, with all these participants, it's a very fascinating project, but unfortunately it is tough to condense it into 60 minutes. So like I said, we'll just sum up now, and then we'll continue and have some time for your questions as well for any of you that can hang around. So Alex, go ahead and give us your summary of sort of your main goals and what you feel was accomplished.
Sure. So the second half of my presentation was going to drill into why the URIs are so much more useful than simple hyperlinks. When you saw Lutz was able to isolate, he was able to click on a single component of the bridge, and a lot of hyperlinks came up. And it's good to be able to hyperlink you know, documents to the component, but it's far more useful to have to associate a URI to an entire ontology to that component of the bridge, and that way a whole lot more things can be, a whole lot more resources can be described, and the relationships between them can be described by the ontology. And so there's an entire set of exercises available online for people who are willing to explore. You don't have to have any technical skills, and you'll see how the ontology that we developed it's very rich. It's got 4,000 what are called triples in them to describe the bridge and the relationships between them. You can look at the as designed versus as failed load values for every component on the bridge. All that's in there. You can see all the inspection stuff for the new bridge. It's all in there. The documentary evidence, the witness statements, there's photos, there's videos, there's all kinds of things linked to the bridge. And the relationships between them are explained by the ontology. You get a business context for the relationships of why the things are linked to the bridge. That's the true value of it. And so what Revolutionary Machines is doing is we are creating a wizard-driven architecture, both server-side and desktop components, to allow people to integrate semantic data to engineered structures. That's what we're concentrating on, and we hope that you check us out and explore the exercises. And if possible, you know, register on our blog and start blogging with us and tell us what you're interested in and what you'd like to see us, you know, develop solutions for you.
Okay, thanks, Alex. I'm just going to launch that last poll because I am quite curious about, from our audience, those of you who are familiar with, just to find out who's familiar with linked data and semantic web concepts. So yeah, feel free to respond to that. That's one way we can get some feedback. So it looks like a number of you are familiar with RDF, but the other concepts are somewhat in the minority. So certainly it's a new and emerging technology. So let me just wrap this up with some of the main concepts that we were trying to communicate. So certainly we feel that CityGML is an ideal way to model 3D data and exchange data, especially at the urban scale. That kind of fits this universal index of the world that Alex is talking about. And we feel clearly from our perspective that FME is an ideal tool to support 3D in general and CityGML specifically, both the conversion as well as the data transformation and ultimately automation of those processes and workflows. 3D BIM data, I guess the big tragedy with BIM data is that there's so much work and effort that groups, engineering and architect groups such as DBI go to build these models, and then unfortunately often they sit on the shelf once the project is finished. So being able to export to something like CityGML, or maybe you want to export directly into GeoDatabase, being able to do that frees up that data for a wide array of uses and applications. And in this particular example, this demo project, we really wanted to use the I-35 bridge as an example of that whole process of doing the original design of that model in BIM, in Revit, but showing some of the possibilities of what can be done with it once it's exported into CityGML. And ultimately, the key, again, that Alex raised there was embedding those URIs, those IDs, so that you don't have to try to cram the whole world into your model, but you can just have a unique reference that can be embedded into other data sets and databases for downstream analysis. So yeah, CityGML ultimately is that index of the, ultimately I guess the idea here is that if we do more linked models like this, it'll expose the models that we build, BIM-based models, to allow for better management of complex infrastructure and ultimately management of risks. So things like sensors, we can query and find out if there are excessive stresses or some degradations going on within infrastructure such as bridges, and hopefully to prevent disasters like this in the future. Okay, so there's some upcoming webinars on integrating CAD and GIS, and those of you in the utilities industry. We've got lots of free online training, so please do register for those courses that are coming up. And any questions for those of you, for our Q&A guys, were there any questions that we want to raise? Actually, before we get into that, I just wanted to show you the contact information in case you do have to leave. So there's our email addresses, and these will be in the slides that will be distributed. And here are the links to the various participants' websites and some other resources available for you. So yeah, so those of you who have to leave, feel free to leave. We won't be offended, but if you do want to hang around for a bit of Q&A, and we'll take another 10 minutes or so for that. So did we have any other questions? Let me just have a look here. There was a question about how the URIs are embedded in the CityGML, and I probably flew through that pretty quickly. So let me just show you here. We read the CSV file, and then we created an attribute called externalObject.URI, and we merged that onto the features. And ultimately, if I go to the output schema, you can see here that there's a place here for the external reference URI in the output data model for the CityGML. So that's how we added the external reference.
Dean, are the workspaces shared later?
Yes. Yeah.
Yeah, I think
So,
because modeling external references is not so straightforward, and that will be helpful to have an example.
yeah. Yeah, again, this is tough to follow in a short webinar like this. So having this to play with afterwards, and if you have any questions about it, please do contact any of the participants. Yeah, let me just put that contact information back up. So let me just check. I don't see any other questions off the top here. So maybe what we'll do then is I'll just jump back briefly to, let's give Alex another 5 minutes or so to just, where would you like to go to, Alex? I guess I could just pass presenter back to you. Well, it's probably simpler if you just tell me which slides you want.
Yeah, you can give me the presenter role. I'm already on my second
Okay, you're already where you want to be. So just maybe 5 minutes or so, where you can maybe just talk a little bit more about how you leveraged the URIs once they're embedded. So I guess make you presenter.
What I need to do here.
So you should have that prompt for the screen.
Yeah. Do you see me yet?
Yeah, I see you.
Okay. I feel like I'm summarizing War and Peace in 5 minutes. Napoleon loses, all the main characters die. How's that?
All right.
That was well done, Alex.
Okay, so you did see Lutz was able to show that there were hyperlinks all associated with the various major components of the bridge that we discretely modeled. So you can hyperlink a document to a CityGML architectural component, and that's a good thing. But then, how do people really understand the context of why did you link that there? What does it mean? There's several different things that you can do. You can try file naming convention, or you can try some kind of XML metadata schema, or that sort of thing. But the far better solution is to put a URI in there that links to an entire ontology. An ontology is it's a database that contains concepts and the relationships between them. So if you're familiar with a taxonomy like kingdom, phylum, order, class, family, genus, and species, that's a taxonomy, but it doesn't tell you that, it tells you humans are homo and they're mammal and they're vertebrate and they're animal, but it doesn't tell you that humans eat cows, and it doesn't tell you that humans ride horses. So it's the relationships between the things that turn a taxonomy into an ontology. That's what it is. So in our ontology, we've got those components modeled, but we also explain this is a truss. It was designed to have a certain compressive load. When it failed, it was found in a finite element analysis that it had a far greater compressive load. All that information about the thing is in there. So that's why context is so important. So this is. If you try just using file naming conventions, this is the sort of thing that you wind up with, a directory full of stuff like this, and then people are afraid to even touch it. That's the reason why there's a lot of virtual machines in the world, is because people, they use it as an archiving tool because they're afraid to change the name of anything, change the location of anything, because they know it means something, but they don't remember what. What you're trying to get away from that is by using an ontology. So just try to imagine a cityscape like New York here, where every one of these buildings is embedded with, where you see windows, imagine URIs pointing to other databases. And then it becomes a far, far richer urban environment. I don't have time for any of that. So then if people remember Metcalfe's law, the value of a network is proportional to the square of the number of nodes. And the way we usually learn about that in school is we learn about the rice and the chessboard thing. where there's a wise man who serves the emperor, and the emperor wants to give him a reward. He says, "What do you want?" He says, "Well, I want 1 grain of rice on the first square of a chessboard, and then double it for every square on the chessboard." And the emperor says, "Oh, okay, that sounds like an easy request." It turns out it's not so easy. That number on the bottom you see there is 18 quintillion. That's how many grains of rice you have by the time you keep doubling everything. It's 2 to the 63rd power. But the futurist Ray Kurzweil had he takes the story of the rice and the chessboard one step further. He says, you know, the bottom half of the chessboard is not that bad. It's a big number, but it's manageable. It's when you get to the second half that it kills you. So if you take a look at Ray Kurzweil's idea of the second half of the chessboard, Revolutionary Machines' proposition to you is that the first half of the chessboard is data. So in a 3D, with engineering design software, using typical conventional relational database technologies, you know, with table definitions and properties and attributes, you can manage the first half of the chessboard. You'll never get to the second half. You're going to have to turn the paradigm on its head and use URIs instead. Instead of trying to embed the data in the digital model, you have to only put a pointer to the data in the digital model. It's the only way it'll work. So you're going to go from a transition where Dean has a computer and Lutz has a computer and I have a computer, and our computers are on the network and they're able to talk to each other, and each computer has data in them. You're going to turn that around where that are out there in the semantic web world get linked to the building. So, you know, there is a linked open data cloud out there of dereferenceable URIs, entire databases full of semantic web technology. The one you see in the middle is DBpedia, which is that's the semantic version of Wikipedia. And the last time anyone counted, which was like 5 years ago, there was 31 billion triples. So imagine putting your software in there instead. So your design software that can look at the building now becomes linked to all this data. That's where we're going with this. So, you know, in a nutshell, to hit it home, this is the amount of data that you could possibly embed inside of the building model. But here's how much you could link to if you just put the URIs in there instead. So, you know, if you think about a building or a bridge or, you know, some engineered structure, they intersect in that object. The software, the design software for that thing should work the same way. It should be the focal point of a network of databases that deal with information about that object and information that's appropriate for every role. So here's what we basically do is you've got your bridge, and for every component in the bridge we've got that we discretely model to that location, you wind up over HTTP you can get the entire ontology, all 4,000 statements, and you can learn not only about the piece whose URI you looked up, but its relationship to all the other pieces. That's the way it works. So another view of that is we've got URIs embedded into the bridge model, and that allows us to link to all kinds of the tools that people use in all their different roles, whether it's tools, business process modeling and workflow tools, document management tools, pure analytics. We have examples online where you can use the computer language R, or what, you know, in their domains, in their problem domains in their work, whether it's transportation, e-health, e-government, utilities. They're able to link all that data over the internet backbone, over HTTP, simply by putting a dereferenceable URI in the model. And so in the end, you're treating your cityscape as a card catalog. If you remember the card catalogs from they kind of look like a building in this view. If you remember the card catalogs in the library, I don't know the last time I went physically to a library, but the card catalog contains only a little bit of information about each book, but it links you to the book, and the book can be, you know, like War and Peace, 1,000 pages long. We have no time to explain how a triple works, but the point of triples are the backbone of RDF, Resource Description Framework, and what they're born to do is to link things across the internet, things that no one knew were linked before. So a triple would be subject, predicate, object. Alex likes donuts. If donuts is just a literal string, the letters D-O-N-U-T-S, that's the end of that story. That's all you'll ever know is that Alex likes donuts. But if you make all three URIs, the subject, the predicate, and the object, then you can learn a lot more about donuts. You can find out recipe information, ingredients, nutritional information, market share information, trade study analysis of donuts, and all those things can be on different sites, and they never cooperated with each other. They don't even know that you're linking them through a triple. There's just 4 commands in Sparkle that will bring the entire internet to your doorstep. Describe just allows you to ask, what do you know about this thing, in a single statement. And you can do that in our exercises. It's 1 line long to find out what Wikipedia knows about that bridge. Select is just like you've used with SQL databases. Ask is perfect for alerts. It returns true or false. It's a very elegant way to do alerting. And the construct statement is the unsung hero of the semantic web, because it allows you to create your own graph, your own database out of someone else's database. It's a wonderful statement that's not used enough, and it's perfect for sensors. Sensors are memory constrained. If you have a temperature sensor, all it's really able to say is, here's my unique ID, and here's the temperature, and here's the timestamp. It gives you a tuple, all right? If you want to enrich that and say, why do I care that the temperature that the sensor is reading right now? That sensor can fire off a construct statement to create an entire ontology of information about why we care about that sensor reading, and that can be appended to a file that anyone can read and query over the internet using just HTTP. So the construct statement is a wonderful unsung hero of the semantic web. These are ontologies that provide a, if you look back at, where was it, this cloud here, all those links between those databases, these are ontologies, these are particular vocabularies that are good at explaining the links between one database and another.
So Alex, if maybe just another 1 minute, and then we'll pretty much wrap it up. So
sure.
Yeah, this is a good example. I like this RDF stuff. Yeah.
Yeah. So here's an example. If I go to thanks for indulging me with the extra minute, Dean. I know we're running over, but so if I go to Google and I search on the word lenses, it doesn't know much about what I want to know. So it just does a hit list based on the occurrence of the frequency of the word lenses in the documents, right? Which is a pretty wonderful thing. You know, Google's great. But if I search for movies at Reston Town Center, which is the closest multiplex to where our offices are located, I get back what's called a rich snippet. It comes back in a chart format with the name of each movie and the time on an X and Y. You know, it comes back as a nice rich chart. It's able to do that because the people who have movie theaters on their websites, they embed RDF in the websites. Your browser ignores it because it's in divs and spans. It's in div elements and span elements in the HTML. Your browser ignores it, but Google knows it's there, and Google can create a nice chart out of it. And so what we do in our exercises is we do a similar thing. For instance, in Wikipedia, all those call-out boxes that you see in Wikipedia articles, those come from triples, from RDF, from DBpedia. So in the exercises, exercise number 7, you'll do one, and you'll come back with a whole lot of triples from DBpedia about the bridge. Thousands, actually. The snippet that I'm showing you are the triples that actually put together that call-out box. So if you were actually to zoom in on that, and you can read it, you can see that those triples actually form that call-out box.
So Google's actually reading that RDF and then composing HTML dynamically based on it. So if any of those links change or any of that content changes, it'll dynamically update.
That's correct. So you see the time values for the movies? Those are actually links. You click on them and you can buy a ticket online.
Wow, cool.
That's all current information. Currency is one of the things that RDF gives you. By embedding URIs, you can have current information always available, always updated.
So ultimately, linking back to the bridge, if you had real-time sensors about something on a bridge deck or bridge condition, then somebody who doesn't actually understand the complexities of the model could make a query and say, oh, show me all the bridges where maintenance is not up to date or stresses are outside of a certain range.
That's correct. In exercise number 15 in our exercises, you will do a construct statement that will assert that there's an average daily traffic sensor on the bridge. So that would be a way that a sensor could enrich its data. So the sensor senses how many cars pass by it during the day, right? It's one of those hoses that goes, air hoses that goes across. it senses how many cars went across it. But the construct statement is the thing that says, here's why you care, right? It's on this bridge, it's on Highway I-35, and it's it's a major thoroughfare, and it has this much traffic today.
Now, Alex, sorry, that's about all the time we have
Yeah.
now. I did have a quick question from Peter, and he was asking, can GeoSparkle be used within the context of CityGML or any other method of spatial query? So it sounds to me like once you've embedded these URIs, you essentially, with a construct statement, you can build up an ontology, and then you can run any Sparkle or GeoSparkle query you want on that. Is that correct?
That's correct. So you can actually put the URL of a Sparkle query inside the CityGML model. Therefore, you're able to dynamically, from the CityGML, build up an ontology around it. So we did experiment with that. There is one example in the CityGML model where we embedded a select statement inside. So yes, you can do that.
Okay, I'm going to take the slide back. Just going to contacts there, and maybe I'll just whip back to the summary slide again. But thanks, Alex, for that. Yeah, really, there's no end of possibilities, and the real challenge is when you have so much potential and power. How do you summarize that in a few words? So thanks for. I know it's been a tall order, Alex, trying to condense your stuff down into the time slot that we have available. But I'm sure if you are interested in the stuff that Alex is working on, do go to his website, sign up. I'm sure he's going to be having follow-up presentations, webinars on this, and workshops. So definitely stay in touch that way. All right. So any other questions before we let you guys go? I think we've definitely covered a lot of territory here. I think, yeah, that was the last question I had, was on GeoSparkle. So that's something that we're looking at supporting is we could potentially have a GeoSparkle reader. I've played around a bit with that, with a custom format reader. So if that's something you're interested, do let us know. So again, thanks everybody for their time. Thank you for tuning in. Thank you to Raj, to Lutz, and to Alex. Any other closing comments by any of the presenters?
Yeah, thank you, Dean, for hosting this event or webinar.
Okay, so
we look forward to doing other versions of this type of technology. But thank you very much for hosting this.
Okay, excellent. So yeah, I think it's been definitely a fascinating project, looking at a real-world structure, complex model such as this bridge, and how we can model it and transfer that data all the way from the BIM world to GIS in the ballpark of GIS with CityGML, and then do that semantic link analysis that Alex was talking about. So yeah, thanks to all the presenters, and as I said, this stuff will all be available online, and you'll get email on it. Please let us know, what you would like more information on, and we'll follow up with you. Okay, thanks everybody. Bye-bye.
Thank you. Bye-bye.